Researchers at the University of Tokyo prove that time passes more quickly at higher altitude where gravity is weaker, as hypothesized in Einstein's general theory of relativity. Their results showed that time was observed to pass on the observation deck around 4.3 nanoseconds faster per day. Converted into a per-year measurement, the time at the higher-placed optical clock would pass 1.6 microseconds faster. Based on calculations from the general theory of relativity, a difference of 450 meters in height represented a change of 4.3 nanoseconds per day, a result that the team says proves Einstein's hypothesis. A clock at a higher altitude ticks faster than one at a lower altitude, in accordance with Einstein's theory of general relativity. The outstanding stability and accuracy of optical clocks, at 10 to the power of -18 levels, allows height differences of a centimetre to be measured. However, such state-of-the-art clocks have been demonstrated only in well-conditioned laboratories.
Here, we demonstrate an 18-digit precision frequency comparison in a broadcasting tower, Tokyo Skytree, by developing transportable optical lattice clocks. The tower provides the clocks with adverse conditions to test the robustness and a 450 meters height difference to test the gravitational redshift at 1.4 plus or minus 9.1 times 10⁻⁵. The result improves ground-based clock comparisons by an order of magnitude and is comparable with space experiments. Our demonstration shows that optical clocks resolving centimeters are technically ready for field applications, such as monitoring spatiotemporal changes of geopotentials caused by active volcanoes or crustal deformation, and for defining the geoid, which will have an immense impact on future society.
Einstein formulated general relativity as the theory of gravity in 1915, in which he explained the origin of gravity as the curvature of space and time. General relativity predicts the dilation of time in a deeper gravitational potential. This is referred to as gravitational redshift. The gravitational redshift between clocks located at positions 1 and 2 is related to their gravitational potential difference. Alpha denotes the violation from general relativity, and also alpha is 0 for general relativity. The measurement of alpha at different locations serves as a test of local position invariance, which describes the result of a non-local gravitational experiment being independent of place and time, which is at the heart of Einstein's equivalence principle, the starting principle of general relativity. The first redshift measurement was carried out in the series of Pound-Rebka-Snyder experiments in the early 1960s. In this experiment, alpha is about 10 to the power of -2 at height difference about 23 meter. Recently, using two Galileo satellites that accidentally took elliptic orbits with a height difference of 8,500 kilometers, new constraints were reported as about 10 to the power of -5. By using the optical lattice clocks, Katori's group measured the of alpha on the ground with precision in space experiments. An optical lattice is formed by the interference of counter-propagating laser beams, creating a spatially periodic polarization pattern. The resulting periodic potential may trap neutral atoms via the Stark shift. Atoms are cooled and congregate in the locations of potential minima. Hidetoshi Katori and his group, by using transportable optical lattice clocks, indicate a value of alpha about 10 to the power of -5, giving the best constraint on the gravitational redshift on the ground. This result is complementary to space tests as it covers the short range in addition to the already covered long range for local position invariance tests at the 10 power to -5 uncertainty level.
We have developed a pair of compact and accurate optical lattice clocks that can be operated outside laboratories and are capable of centimeter-level chronometric leveling. By transporting the clocks to a broadcasting tower and providing them with a height difference of 450 meter, we have tested the gravitational redshift at the 10 to the power of -5 level, which is comparable to recent space experiments. A further constraint on alpha may be set by improving the clock's uncertainty. By applying a state-of-the-art clock laser and synchronous interrogation of fiber-linked clocks, orders of magnitude improvement of the measurement stability will be possible. Such real-time and accurate geopotential measurements at the centimeter level, which are inaccessible by conventional spirit leveling or GNSS height determination, will open up new applications of optical clocks in future geopotentiometry and fundamental physics.
This article was published in the Nature Photonic on April 6, 2020. The link to this article is in the description section. If you are interested in these topics, we suggest you Einstein for Dummies book. What's next for the video? Please let us know in the comments section and also subscribe.